my talk. Talk about the improved bounds for the US+1 norm and some applications. First of all, I'll start with Zarides theorem. So basically, it says that if you have a subset of the natural numbers which has positive upper density, and for each positive integer k, it has a non-trivial arithmetic progression. Non-trivial means non-zero common difference. Second, what I'll talk about is the Green-Tau-Ziegler linear equations in primes result. It states that the number of arithmetic progressions in primes it isn't exact asymptotic. Exact asymptotic is on the slide, and this integral I is, you could think of that as like roughly n squared over log of n to for quantitative bounds for Zarides theorem. It's not super obvious to do it at first value, but the way you would do it is as follows. What you do is you let R sub k of n be the size of the largest subset of 1 to n out k term arithmetic progressions. And then what that result from before implies is that R sub k of n is little of n. So for quantitative bounds, you could ask, what can you say beyond like little of n? Would be a bit more specific. The first quantitative bound in general, or reasonable quantitative bound in general, is due to Gowers in 2001. R sub k of n is n over like log n. In general, we have a lower bound of n times quasi-polynomial n. This is due to Berend. For k equals 3, there's kind of a long line of work, and it's culminated in Bloom-Sisask result and Kelly-Maker results. Basically, eventually establishing these quasi-polynomial upper bound, so that the quasi-polynomial lower bound and upper bound is. In general, we conjecture that the upper bound for R sub k of n is the Berend bound. Still quite far from it. Finally, previous result we have is R sub 4 of n, which is n over log of n to Green tau in 2017. So that's how you quantify Zarides theorem. To quantify linear equations, you could do more straightforward. What you do is you take this little one that I had earlier, maybe be a bit more specific. And previous work is Tau and Teravainen in 2021, who proved a double logarithm upper bound for that error. So our new results. So our first new result in this direction is improvement to Gowers' upper bound for Zarides theorem. So we get a quasi-logarithmic bound. And the second new result is so this actually does use like input from my work with Asher and Matab. So I get this strongly logarithmic upper bound on the error term. In general, this error term would be ineffective in A, since C goes 0 issues. So there's sort of 3 sources for improvements. So the first like primary like source of improvement is the quasi-polynomial sum-set result. Um, Second one is the improved estimates on equidistribution of nil sequences or exponential sums of bracket polynomials. The third result is the quasi-polynomial inverse theorem. So I got the U4 one in 2023, and me, Ashram, and Top got the general one a bit later. And so most of my talk will focus on part 2. So the second one, which would be on computing exponential sums of bracket polynomials. Yeah, I think Matab's talk will focus on a bit more on proof of the inverse theorem, assuming this equidistribution. So, just as a reminder, here's the definition of the Gowers norm. So what you do is you take a finally supported function over your group, which in this case is z. You average it over, you average it like special way over these like s+1 dimensional parallelepipeds. And you take in 2 to the s+1 root, and you get the Gowers function. So for instance, the U4 norm is defined like this, as pictured. Before, we can also define these Gowers norm localized to different sets. So the Gowers inverse theorem states that if I have a one-bounded function with more Gowers norm, then you correlate with a nil manifold of degree s. Here are some other parameters, most notably dimension and complexity, and also this correlation parameter. The result is qualitative. They don't give these parameters like m, d, and epsilon, k. Is very weak information on quantitative dependence. Right. So it's been said before, the inverse theorem is a theorem that has its roots in organic theory. Something of multiple organic averages from Raw, Ziegler, and one of the things it does that I find that's pretty amazing is that it associates like an algebraic object, which is the like no manifolds, no sequences, the Gowers norm, which is purely analytic. So for quantitative bounds, we have first work of Freddie Manners in 2018, which basically states that we may take this dimension parameter to be polynomial in delta and all the other parameters to be double exponential. So what we have done is we have improved all these bounds. So what we could do is we could take the dimension bound to be log of 1 over delta to the power, and all the other bounds to be the correlation bound, the Lipschitz bound, complexity bound of no manifolds, which yeah, I won't really define any of these terms in this talk to be and so what I will focus on is really these the new equidistribution theorem, and I made it a point not to define any notation on nil sequences. Instead, I will just try to give like an intuitive overview on how this works, and maybe like the best language to use is the language of bracket. So first, I will let E of x define like the complex exponential, exponential of 2 pi x, I will define this expectation over n parameter to be this averaging operation over 0 through n minus 1. And I will let this square bracket be the nearest integer to x rounded up, and the curly brackets x to be x minus the square bracket x. And yeah, an example of an exponential sum we would study is an exponential sum of alpha and square bracket beta. But maybe more generally, we would want to control exponential sums like b of n for any real bracket polynomial. B of n is basically any of these examples, and anything you can create with a bracket and a polynomial operation, like a square bracket or a curly bracket operation, method I have should be able to, with some cheating, should be able to handle it. So first thing is that consider this exponential sum, where I have an expectation over just like a single, like a single like quadratic bracket polynomial phase. I call this quadratic because it's like this kind of looks like a degree 2 object, except that one of the things is in a square bracket. But in like locally, it does behave like locally over like some Bohr set, if you know what that is, it behaves like a quadratic polynomial. So right, so if alpha and beta are both equal to 0, then this exponential sum is just summing over one function, so it's going to equal 1. So the conclusion is you can't really have a non-trivial uniform estimate on exponential sums of all bracket polynomials. However, we can hope to prove some inverse type estimate. Say if like suppose that the absolute value of this exponential sum is sufficiently large, then what can we hope to say about alpha and beta? And whatever information we say about alpha and beta, it sort of has to include the case where alpha is equal to 0 and beta is equal to 0. So kind of the result in the literature in this direction is the Green-Tau equidistribution theorem, which basically says that if this exponential sum is large, then there exists integers k1 and k2, which are bounded, such that k1 alpha plus k2 beta is going to be really small. It's like 1 over n. So here I'm going to use this rough notation of this double less than or equal to sign. Less than sign will be a double less than or equal to b is a is less than or equal to constant times b. Here this norm, this R mod z norm is the distance from x to its nearest integer. So that's previous literature, but maybe like a more representative example of the situation would be if instead of like a single bracket, we had a sum of like d many brackets, then the result is then if I sort of quantified the result in terms of d, I would get a bunch of double exponential parameters d. And maybe the question is, can we do a bit better than that? because for applications, one really cares about the dimension dependence. And it turns out that like yeah, like the applications were just like bad enough so that when we fed like we're just bad enough that it was like lossy to apply this equidistribution theorem. Like if these bounds were sort of just single exponential in dimension, then sort of applying the equidistribution theorem wouldn't be wouldn't really be lossy at all. But somehow like every time you apply this equidistribution theorem, you loss a law. And yeah, I mean, and in these like in these applications, we were sort of applying these equidistribution estimates many times, each time losing a log, and then basically compounding to an iterated logarithm loss. So one really would hope for something much better. So these bounds are double exponential in dimension, meaning that their exponent is the exponent is exponential in dimension. And similar bounds happen for if you cheat a bit for exponential sums of arbitrary bracket polynomials. And so, yeah, I mean, a major obstacle to prove like these, to improve on this like double exponential bounds in dimension is something called induction on dimensions. What it means is that like a lot of these equidistribution theorems are proven is by sort of arguing inductively on dimension, simplifying like your bracket polynomial. By dimension, I meant like this D parameter for sure. So simplifying your bracket polynomial one dimension at a time until until it was sort of simple enough to analyze by hand. And a major disadvantage to doing that is if on like any time you simplified the bracket polynomial by like one dimension, you had like a parameter decrease of like delta goes to delta squared. That will iterate to delta to the 2 to the t. So that's pretty bad. And we would want to avoid something like this. So that is what I managed to do. What I've proven is I've proven a version of their theorem with these improved dimension bounds. In fact, in order to prove this, I needed a much stronger statement that there are quote unquote enough linear relations to reduce to a lower degree bracket. What that means, I will try to explain later. Are there any questions at this point? So the rest of the talk will be roughly a proof of this theorem, or a sketch of the proof of this theorem. We're going to start with our bracket polynomial with like a sum of like d of any of these quadratic bracket polynomials. And then I'm going to let S be the exponential sum over it. And suppose I have that it's very large. Then the first step you do is kind of the first step you would do if B were like an ordinary polynomial. You apply like the Van der Korpen inequality. What you get is that there exists a bunch of h's inside 0 through n minus 1, such that this exponential sum of b of n plus h minus b of n is large. Okay, but this this doesn't really look like it helps at all, but what you could do is you could do the following. So b of n plus h minus b of n is the sum of a bunch of terms that look something like this. So the second term looks like reasonably simple. This first term looks a little ugly. Okay, what we could do is we could just use a distributive property on like the first term. Then what we could do is we could pretend that we can use a distributive property on the second term. Except we have to remember that it doesn't quite distribute, right? You get kind of like an error term that appears, and when you apply the distributive property, but somehow these error terms are manageable in some way. So one way to see this is that what you could do is you could write these error terms as a sum of a product of two bracket things. And so what I'll present is kind of a method on how to analyze E of like a bracket product of two things. So this is how you do it. So what you do is you consider a function h of x comma y to be equal to E of x times y. Then you can view h as like a piecewise smooth function on r minus z squared by identifying minus 1/2 squared with r minus z squared. That's kind of an unusual thing to do because you may just think of h as a smooth function of r squared, but just go with it. Now, modulo some issues near the boundary, what you could do is you could approximate E of bracket alpha n bracket beta n in L1 of n by some f of bracket alpha n comma bracket beta n, where f is smooth on r plus z. What you do is you just take this this function h, which is like defined on the square, and you just cut it off. You just cut it off like near the boundary. You take a function which agrees with this h on like most of the square, and the remaining square you just cut it off. So this won't really have the discontinuity issues, but the problem that could happen is that this when you cut it off like this might not be a good approximation, right? You might have some issues near the boundary, like alpha n and comma beta n could be basically distributed near the places you cut off at. But that's kind of a purely technical point, and there are a number of ways to handle this. So what you do is you take your smooth function f and you just Fourier expand it into a bounded number of Fourier coefficients plus some small error. And the key point of doing this is that now each of these coefficients, I have like k1 bracket alpha n plus k2 bracket beta n. If I raise it to a complex exponential, these brackets basically, so we remove the brackets. So this is kind of a general procedure on how to handle problems with two brackets. So one thing I'll remark is, and what this doesn't really quite prove is that if I have d many brackets, this operation loses at most delta raised to some polynomial in d. Actually, so the procedure I do, if you iterate this many times, you would get like delta to the exponential of d to sort of get this like polynomial in d in the exponent. You have to, instead of iterating this many times, you kind of do it all at once. you construct like the bigger h in the beginning, and you sort of do it all at once. And because these factors are sort of exponential and or have an exponent polynomial dimension, these are okay factors to lose. So basically using these terms, maybe like a summary is that I have b of n plus h minus b of n. I could write that as a sum of a bunch of bracket polynomials. Just really use the distributive property, and then you have to add a bunch of terms to the end, which are these like products of two curly bracket lower order terms. Yeah, and then what you do is you just Fourier expand all these lower terms, like I do. And you'll lose like something with exponent polynomial. Right. So first, because we're taking absolute value, the e of like alpha h bracket beta h don't matter. They don't depend on n. So we could just discard all of them. And so what you do is you take your bracket polynomial. What you want to do is you want to write them as basically a linear phase in n plus like a bunch of lower order terms. And there's a way of doing this by careful bracket analysis. And what you get is zeta n dot product gamma h plus a bunch of lower order terms. Zeta is like you take your first bracket phase like beta minus alpha, and gamma would be like alpha and beta. So that's what you could do. And okay, so applying this, we have like e of zeta n dot gamma h, plus a bunch of lower terms. It's gonna be large after, this is a step right after, like this, the step right before this is like e of b of n plus h minus b of n. So that's what we did. Then what we're gonna do is we're gonna Fourier expand the lower order terms like I did before. Some a bunch of Fourier coefficients, and crucially, the L1 norm of these Fourier coefficients is going to be bounded by something single exponential dimension. If I apply the pigeonhole principle, you could find some alpha prime such that this exponential sum holds. And now you could compute this exponential sum directly by using the geometric series. So what you get is that zeta dot bracket gamma h plus ch minus plus alpha prime is that's really close in integer. And any questions on these manipulations? Okay, so what you do here, so Green and Tao showed in 2007 that suppose we have a bunch of h's that this occurs, and either a is really small, or you could find some eta that's bounded such that eta dot alpha is really close in.
Isn't this what you showed? Didn't we have weaker bounds than that in the exponents?
Okay, yeah, sorry, I actually lied back there. Sorry. Yeah, so the bounds you get here are actually like this, but somehow what I really needed for these single exponential bounds was this much stronger statement, and I didn't really want to state my much stronger statement over here. Sorry about that. I lied a bit. Such that eta dot alpha is really close to So what I showed is kind of a refinement of this. So what I showed is that that's kind of not the only thing that could happen. The other things that could happen is that a um, a satisfies a bunch of linear constraints, and like alpha dot a bunch of linear constraints is really close to an integer, and these like linear constraints are all like orthogonal to each other. They're all bounded, and like all my losses are sort of single exponential. So I'll make the remark here that I will state results and prove results in a way that maybe would make like most like intuitive sense, but won't really be. I may sacrifice some quantitative bounds to do so. So so this is the step where this kind of induction on dimensions is beaten. So here we've sort of found like many linear relations. Kind of makes sense that this is where induction on dimensions is beaten. And what this lemma gives you is it gives you kind of enough linear relations on alpha beta so that when you simplify like this original bracket polynomial, or like this bracket polynomial that I have there, it and like when you sort of plug in these like linear relations in there, this kind of bracket polynomial becomes like a low order term. Becomes like a sum of a product of a bunch of products of like curly bracket terms. And the other thing I can say is that one can, if you cheat a bit, one can bootstrap this procedure to compute these exponential sums for arbitrary bracket polynomials. You just use a Van der Korpe inequality, Fourier expand the low order terms, and then like bootstrap this lemma a bunch of times. You use induction. This will give you a procedure to do any exponential sum estimates for arbitrary bracket polynomials, provided you cheat a bit. And the cheating is like, it's kind of like this issue I described before with like the distribution of it's what happens like when things are not nice, like when your phasors are not nice and you're sort of distributed near the boundary. Somehow, if you deal with like smooth objects like I deal with in my paper, none of these issues actually happen. They don't cheat. So here is a sketch of the proof. The idea of this proof is to iterate the regular bracket polynomial. So iterate this this lemma over here. So suppose that a dot bracket alpha h plus beta, that's really close to an integer for a bunch of h's. Then if a is small, then the iteration terminates. And the reason why it terminates is that a is small is kind of included in this case, right? A is small would give like d is equal to r is equal to d, and then each of these wi's would be like the coordinate vectors, the standard coordinate vectors. So like ei dot a would be like the ith component of a. That's going to be really small. And then the alphas, you can't really say much about the alphas. That's kind of enough for this. So that's so that would be a valid termination for this lemma. Okay, if each component of a is not small, then what you could do is you could find some linear relation bounded linear relation that alpha satisfies, or alpha like roughly satisfies. Or in other words, eta 1 alpha 1 plus eta 2 alpha 2 dot 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 plus eta d alpha d. That's going to be really small. So suppose for simplicity that eta 1 is equal to 1, and that this curly bracket were a genuine equality. What you do is you write alpha 1 in terms of alpha 2 to alpha d. So I have like alpha 1 plus eta 2 alpha 2 plus eta d alpha d is equal to 0 mod 1. And what I could do is I could write alpha 1 as minus eta 2 alpha 2 minus eta 3 alpha 3 minus eta d alpha d. And okay, then what you do is you just insert this back into this bracket polynomial expression. And if you sort of just cheat for a bit and pretend that like brackets were genuinely additive with like no remainder at all, you'll get like a dot like alpha h is equal to a tilde dot alpha h, where a tilde I have is defined like this. Right. So the point is that like because we use this information to because we use this information to like write like alpha 1 in terms of like alpha 2 to alpha n, alpha d, like the alpha 1 coefficient like no longer appears, and we could sort of lower the dimension of the overall configuration by 1. But unfortunately, brackets aren't quite that nice, and you do get like this remainder term. And this remainder term P of H, now this remainder P of H will always take integer values. So this is because alpha 1 plus eta 2 alpha 2 plus dot dot plus eta d alpha d, this is 0 mod 1. This is always an integer. Therefore, you take brackets of everything, and these eta i's, these are integer relations. P of H will always be an integer. In particular, because these etas are bounded, P of H will always be a bounded integer. So you could pigeonhole in one of these values of P of H. So what you do is you, there exists one value, one like level set L such that P of H is equal to L, has a bunch of H's that satisfy it, right? Has like delta over the number of like values of you're pigeonholing it that satisfies it. And so what we could do is we could pass the hypothesis that a tilde dot alpha H plus beta tilde is really close to here. A tilde will have first coordinate equal to 0. So that this kind of this configuration a tilde dot alpha H will be dimension d minus 1. And another thing, another thing to note is that a tilde, every single component of a tilde is an integer linear combination of components of A. So in particular, you could right. So like when you continue this iteration, this iteration terminates, it'll give you like this like a tilde tilde or like a tilde prime, where every single component is like a linear combination of components from like the previous stage of the iteration. But because like every single one of these terms is also a combination of elements in A, every single term will give you like a bunch of combinations in A, and you'll just have to take my word for it that when this like iteration terminates after say like R many steps, this is what you'll get. you'll get that A satisfies a bunch of linear relations. Alpha satisfies a bunch of linear relations, modulo an integer, and these relations are sort of orthogonal to each other. And there are several problems, like quantitative problems, doing these. So the first problem with this is that the size of like A tilde might like blow up. So recall that I had like I have this like parameter M, and I assume that like each component of A is bounded above by N. Now if you construct like an A tilde from this, you have like a trivial upper bound of like 2 times like the L infinity bound of eta times the L infinity bound of A, right? And the L infinity bound of eta is like bounded by like M over delta to some power. And so therefore the L infinity bound of A tilde is also bounded by the M over delta to some power. And that's pretty bad because this is like, this behaves like M goes to like M squared. This is even worse than that. And if you iterate this d many times, this will give you double exponential balancing function. But the trick to overcoming this is to use Minkowski's theorem. So intuitively, if you look at a hypothesis like this, and like A is not very small, therefore there exists like some like integer relation eta that alpha satisfies. Like eta should be roughly like be close in some sense to A. And so this is kind of what you get. What you get is that eta lies close to the direction of A. And you could prove this by giving a slightly different proof of the result of Green and Tau by taking a tube lying in the direction of A. And if this tube has like large enough volume, if it has like volume larger than 2 to the d, it will contain a non-zero lattice point. And this lattice point is eta. And because eta lies very close to a tube, when you do this like reduction kind of step, this will actually decrease the size of A. So A tilde will actually be less than A. So this M variable doesn't like nothing really happens to it. So the second problem with this iteration is that when I pigeonholed in each of these level sets, that's a bit too expensive, right? Because P of H is like bounded by, like naively P of H is bounded by the size of eta times like D. And the size of eta is like M over delta to some power. So if you pigeonhole H's in one of these level sets, you have like delta proportion delta many of these H's. You apply the pigeonhole principle to one of these level sets, you get a proportion delta over M to some power. That's pretty bad. Again, that would iterate to double exponential. But the trick to do over here is to sort of convert everything into a bracket polynomial and then Fourier expand it. So notice that the level set, each one of these level sets is kind of Fourier measurable. And that the indicator function of these level sets, you could sort of describe in a bounded number of Fourier coefficients. And if you pigeonhole in one of these level sets, this kind of relinquishes this information. So here's how you would kind of, or here's one way to exploit this information. It's the way I found. So A dot alpha H plus beta being really close to an integer for a bunch of H's. This is roughly equivalent to if I take this exponential sum, E of A n dot alpha H plus That's not beta. That should be beta n. Beta n, that's going to be large for also proportion delta many h's. Then, okay, then you could do kind of the same thing as before. Write a n dot alpha h as like a tilde alpha h, plus like some like lower order term. Okay, the lower order term I got was like alpha 1 n times p of h. But crucially, p of h is an integer. So you could replace alpha 1 n with like curly bracket alpha 1 n. And notice that the curly bracket alpha 1 n p of h, so p of h, if you recall, is this thing over here. This is a linear combination of products of two curly brackets. And so what you could do is you could kind of Fourier expand these lower terms. And okay, in order to kind of get to this procedure, I needed to introduce a new variable k. And so what you do is you Fourier expand into lower terms, using that same trick as before, and then you pigeonhole in one of these like in one of these Fourier coefficients, and what that will do is that will shift all the losses to k. And delta does suffer a little bit, but it doesn't really suffer to like delta goes like m over delta to squared or something. It goes like delta, it goes to delta over 2. And so that brings me to the third problem, which is that this loss in k is quite bad. So what you did is you Fourier expanded this into lower terms. This might cost you yeah, k goes to k to the d. And if you do this d times, this will also iterate to double exponential bounds. But kind of the trick to fixing this is to remember the bracket polynomial every single time you iterate. Right. So what you do is you instead of sort of cashing in a bit too early, and like iterate this kind of hypothesis, a dot alpha h plus beta. What you do is you convert it, sort of just think about this problem over here. Remember this bracket polynomial, and then at the very last step, Fourier expand this to get some eta. But when you got the eta, you sort of plug it back in here. You get a different bracket polynomial, but you sort of remember the bracket polynomial from previous iterations. And here, the loss in k no longer becomes like iterative in that like it sort of builds up from a previous k, because you're remembering like this k from like the very first step of the iteration. It's sort of okay. And maybe a key thing is that yeah, the comment I made before is that if you had like d many curly brackets, your losses were only single exponential dimension. And okay, I mean, I don't know if you believe me, but I can tell you that this iteration works, and there are no more problems, and this will give you the refined bracket polynomial. That is the end of my talk.